Now what about heat conduction in cylinders? So far we've talked about just simple flat walls, right? What about in cylinders? Well, in a cylinder you've got a curved wall. How does that change anything? Well, remember Fourier's rate equation is actually a differential equation. And if you think about integrating across the resistance of the wall, as you move from the inner radius to the outer radius, that area available for heat transfer changes. So in the equation where it says equals negative Ka dt over dr, if we want to integrate that from the inside radius to the outside radius, well, we've got a problem because the area is a function of radius, because we're taking infinitesimal strips of the stuff, see? So we have to somehow integrate it. Well, I won't show you all those details. Don't worry about the calculus. Here's the result. The natural logarithm comes from the fact that this is a curved surface and that area increases. So hopefully that's satisfactory to you. But you'll notice we've got the length of the cylinder. Okay, so that's L. So in the pink diagram, that's the depth this way. We've got the thermal conductivity K of the material, and then a geometry factor, essentially 2 pi, and the natural logarithm of the inner and outer radius ratio. So there's the equation for heat conduction in a round cylinder type thing. And this is very common when you're talking about pipes or anything like that. This is an extremely common scenario. So we can write the conductive rate equation for a cylinder in terms of resistance by combining all those terms except for Q dot and delta T and putting them together and coming up with an effective not radius, but an effective resistance for the cylinder. And now that we've got a resistance for the cylinder, we can talk about the entire network, because now we've got, again, 3 resistors in series going from, say, think about it as hot water convecting on the inside of the pipe where it's flowing through, and air on the outside of a pipe. Well, we're going to have resistance to heat transfer within the water inside of the pipe, and that's the first term in our resistance there. And then we've already seen our resistance in the cylindrical wall portion of the pipe. That's the middle term in the bottom of the box. And then finally the last term represents the resistance to convection in the air surrounding the pipe in my example. And then we can simply write the rate of heat transfer in terms of the total resistance and the total driving force for heat transfer, which is the bulk temperature of the liquid inside the pipe and the bulk temperature of the air outside of the pipe. You can do the same thing in spheres. In a sphere, you still have to integrate from inside radius to outside, and if you do that, the equation comes out and looks a little bit different for the resistance in a sphere. It doesn't involve the natural log, but we do get pi, we get R1 and R2 in a mathematical relationship. So there's the resistance. You don't, again, have to worry about the details of integrating it. The point is that we've figured out the resistance of the sphere's shell, and now we can talk about the total thermal resistance and the total temperature difference, T infinity 1 minus T infinity 2, which is the driving force for heat transfer from the fluid that's convecting inside of the sphere to the fluid that's convecting outside of the sphere. And you can see again the 3 resistances simply added together here, because this is simply a series network. Now you might look at this and kind of scratch your head and say, well, okay, this is fine, but it seems a little mathematical, because where would this be used? Well, there's actually 2 places. I've actually used this in my propane tank water storage. Remember the heating system I told you about, where I've got a wood boiler that burns wood, and it's best to burn it fast and hot, so I dump the extra thermal energy into 1,000 gallons of water that's held in propane tanks. Now, I don't hold propane in those tanks, it's just water. And that's a good place to act kind of like a thermal battery and store this thermal energy. Well, the ends of those propane tanks are essentially hemispheres. They're half of a sphere. And it turns out in analyzing heat loss from these things, I could analyze it as a sphere and a cylinder. But that's one place where you basically break the sphere in half, where I suppose if you had a spherical tank being taken out into space so that it's nice and strong and holding whatever, liquid oxygen or something, it could apply there. But here's an interesting one. If you watch Mythbusters, they performed an experiment where they had heard about people's mouths being burned by jawbreakers, and apparently what would happen is people would take the jawbreaker, put it in a microwave to heat it up, and the idea, of course, is to soften it a little bit so that when you chew it, it's not so hard, which kind of makes sense. Then they would take it out, it would be really hot, so they'd let it sit for a while, but then they would take it, bite down on it with their mouth and their teeth, and hot liquid from the inside would squirt out. And it turns out that microwaves don't actually heat from the inside out. They heat from the outside in, really. Okay, yeah, the radio waves do penetrate the outside surface of in this case, the jawbreaker a little bit, but by and large, that heating occurs from the outside in. And so the outside temperature is actually the higher temperature, but once it's heated throughout, remember the users then take the jawbreaker and set it on the counter until the outside is cooled. And it turns out that the stuff inside has a different nature. It lets go of heat differently and it behaves differently. So it basically, the outer layer of the jawbreaker serves as thermal insulation, and the inside stays nice and toasty hot, and then when you bite into it, it burns your mouth. And they found out, yeah, that actually does work. You can certainly make a jawbreaker melt on the inside and remain very hot in the center, and you would burn your mouth in the case when you chewed down on it. So don't do that. So it's sort of a whimsical example of where there could be convection on the inside of a sphere and convection on the outside, and that's what would happen, of course, as the jawbreaker is sitting out on the counter and cooling somewhat. Now, multi-layered cylinders and spheres, I don't know much about multi-layered spheres. I don't have a good example for that one, but I do have one for cylinders. The boiler I told you about, when I first got it, I put it in my garage, built the chimney and everything through the roof, and I decided I wanted to run steel pipe from the boiler right through the wall next to it, and then run a heat exchanger, and then PEX after that. Now, PEX is a type of piping that's plastic, and the manufacturer of the boiler said, yeah, you can hook PEX up directly to the boiler, but I did not feel comfortable doing that. I mean, the boiler might really overheat, and I wanted to have steel right there carrying this possibly super hot, high-pressure water. I wanted steel there instead of plastic to carry it, at least till I got to the heat exchanger inside of the house. So I did a lot of work plumbing with, steel pipe, cutting it to length, threading the ends, making custom lengths, and making sure I had enough fittings and so forth. Finally got the whole thing set up, right? It's getting close to winter time because I'm always behind on my projects and I need this boiler to work. So I finally got it all hooked up and decided, okay, I'm going to build my first fire in this thing and heat my house with it and see how well it works. So I got the fire going, which was a challenge in and of itself, because running this type of boiler is a little different than a regular wood stove, but got it going well. And I could tell I was getting really hot water out of it because I could measure the surface temperature of those pipes that were running into the house, and they were nice and hot. And it was actually quite disappointing that, yeah, in the house with the heat exchanger I had, it was giving off some heat, but it just wasn't enough to heat the house. And I thought, oh boy, what have I done here where I've paid all this money for this boiler, did all this work, put in all this piping, and it's just not delivering. Well, I realized, wait a second, those pipes, those metal pipes, have very low resistance to heat transfer because the wall is relatively thin and it's made of steel. So what if those pipes are removing a lot of the energy? So sure enough, I did a few calculations, and yes, the bulk of the energy was being lost by these steel pipes. So I grabbed some insulation I had left over from when I'd worked on my house, and it was just this fiberglass insulation, and I wrapped it around the pipes. And I'm talking, I think I used 1.5, 2-inch pipe, I don't remember now, pipe about like this. I wrapped this much insulation. It was probably 10 inches, 12 inches in diameter by the time I was done, and I put multiple layers of fiberglass insulation on it, solved the problem completely, and it's been working fine ever since. So that's an example where you might have multiple layers of insulation and therefore multiple cylindrical or spherical resistances. The equation I've included down here for R total is for a cylinder, because as I said, I can't give you a good example of a multiple layered sphere, but certainly multi-layered cylinders are common because of piping. So you see in this case, we've got convection inside of whatever the pipe is made of, and then conduction through 3 layers. Possibly the first layer could be, say, a steel wall, and then 2 layers of insulation, maybe a layer of insulation, maybe a layer that's a different type of insulation, I don't know. And then finally, convection in the last term for 1/H2A4. Now, if you think about what goes on when you add insulation to a pipe, you're actually increasing the surface area where convection is taking place. And so you're actually helping out the convection and increasing the rate due to convection. So is there some critical thickness of the insulation where you're actually shooting yourself in the foot and it's worse than nothing? Actually there is. Let's think about this. R2 represents the radius of the outside of the insulation layer. So in the picture there, the gray area is the insulation. The pink area is just the pipe. Okay, so we've got our resistance to heat transfer in convection. Okay, and we're neglecting the pipe resistance in this example because if it's steel, it's not worth worrying about anyway. And as the radius of the insulation increases, R2 goes up. Well, the first term, which represents the resistance of the insulation, obviously goes up because R2 is going up, so natural logarithm of R2 over 1 also goes up. That increases the insulation resistance. Makes perfect sense. You knew that before you took this class. But look at the second term, which is a 1 over HA term, where A is the area, and the area is 2 pi R2L. Well, in that case, because that area is increasing, since R2 is increasing, the convective resistance goes down. And so you can actually plot the heat transfer rate as a function of R2, the outer radius of the insulation. And it turns out you do in fact reach a maximum, and then it starts to drop off again. Now, most insulating materials that are practical to use have a relatively low thermal conductivity. So you notice that that makes the denominator of the insulation resistance low, which makes that insulation resistance high. This is the goal. That's why you use low thermal conductivity materials as insulation. Now, because of that, and because that term ends up being so large, typically the critical insulation thickness is very, very thin. As a matter of fact, most of the time you don't even have to worry about the critical insulation thickness, because for most practical applications the insulation you add will be much thicker than the critical insulation thickness. But you can calculate the critical insulation thickness. Just take the ratio of the thermal conductivity of the insulation divided by the convective heat transfer coefficient out in the air around the pipe, or whatever fluid is around it, and that will give you the critical insulation thickness, at least for cylinders. In the case of spheres, it's the same thing, but it's times 2. It's just from the math. Don't worry about where that comes from. And I'm not sure when you would need this for a sphere. As I said, cylinders and essentially pipes are much more common. But that's how you calculate the thickness. So you can imagine that the thickness could be some decent amount if K is a fairly high number, right? If K, the thermal conductivity, is really high and the insulation is actually not a very good insulator, well then the critical thickness would be a larger value at constant H. But most of the times, as I said, we use fairly low thermal conductivity materials for insulation, and so critical insulation thickness is usually very, very thin.